Okay, for the last speaker in this session, we have Irfan Siddiqi. Fascinating title is Simulating Topological Band Structure Using Quantum Locks.
Okay. Thank you for the introduction. Can everyone hear me in the back? Okay. I'd like to start by thanking the organizers for inviting me to this extremely stimulating meeting, which is cross-cutting on all platforms. I want to play a little tongue-in-cheek with the title of the conference. This is, to me, also engineered quantum matter. What you're looking at is a chip with 10 quantum bits, all coupled and being read out in my lab. The fundamental quantum properties of this chip are not the subject for the talk at the moment. What I want to describe to you is how we can use this engineered quantum system to study the system that we were, in fact, hearing about in the beautiful experiments this morning, right? In particular about topological behavior of complex condensed matter systems. So that's the subject for today. I want to start by thanking the people that actually do the hard work in all of this endeavor, and in particular, the members of my group shown non-locally entangled in yellow are in fact the authors of the work that we'll hear about. And in particular, I would also like to acknowledge a very fruitful theory collaboration which falls under the auspices of the new quantum center that we've set up at Berkeley. And in particular, this brings together condensed matter theorists as well, so I want to thank Norman Yao for telling us about the linkages with topological physics. So one of the challenges, as we've heard about this morning, is in fact there is a rich phase space in actual natural microscopic materials that one can survey both in terms of their synthesis and in terms of quantities to measure. The alternative approach, perhaps really going back to Feynman, is to consider a Hamiltonian where I can assemble a different quantum system, and in particular if I let it evolve naturally, so to speak, and measure some property of this quantum system, then I will have performed, if you like, a very specialized computation or simulation of interest. In particular, I can break this down a little bit further into two categories. There is one class of experiments, roughly speaking, which is called emulation or analog simulation, where I try to simulate exactly the type of couplings I have in another system, right, with a different set of bases. This is quite challenging on the sense that, in fact, some of these couplings can be very complicated to put in there. Another approach, and this is the one I'm going to talk about today, is really a digital simulation where, in fact, I'm going to drive the dynamics, not simply by natural evolution, but by Hamiltonian evolution and putting in various control pulses. Okay. So this type of simulation is indeed powerful, but the other side of the coin is I need an algorithm to actually go ahead and execute something useful. So these are the two sides of the coin, if you like, between these two approaches. The types of Hamiltonians that people are looking at, in fact, cover the entire phase space of modern physics, if you like. In particular, with superconducting qubits, we're extremely interested in quantum chemistry. And the idea there is there may be a very short way where you can see, in fact, a real advantage to using quantum hardware over classical devices. And if you ask me later, I'll tell you more about that. But that's not the subject for today. In particular, I don't want to talk about chemistry and ground states and reduced density matrices. I do really want to talk about topological invariance. So to go to, if you like, what Seamus Davis perhaps said were conventional condensed matter effects yesterday, if we think about interesting physics happening at phase transitions, whether you go from solid to liquid, normal, to ferromagnet, to superconductor, there is some type of symmetry which is broken, whether that's SU2 spin rotation symmetry or gauge symmetry. For a superconductor, indeed this covers lots of materials, but we know that in fact there are more subtle effects where these symmetries are not broken. Right? The quantum Hall effect is a very classical example, if you like, or quintessential example of this. But in fact something does change, right? And we need a different characterization of these materials. And one can in fact construct, like Alexei Kataev and others, a periodic table based on topological properties or invariants. So the idea then for this talk is how do we go ahead and encode, if you like, this kind of topological behavior in a superconducting system, and how do we measure these topological invariants as well? And that's really the subject of the rest of the talk. So the algorithm that I want to describe is a very different one than usual quantum algorithms for computation and simulation. The origin of this quantum walk idea, we can first talk about the classical random walk. So the very old idea going back at least to 1905, where one flips a coin, right, and then decides whether to go left or right. This particular algorithm, classical algorithm, is exceptionally useful and finds use in Brownian motion, computer science, social networking, finance, genetics, you name it. a lot of things based on classical random walks. The quantum version, if you like, is very nicely penned down by Aronov here in this paper, which considers the fact if your coin, in fact, can be in a superposition, then what would happen? In particular, the coin can be in a superposition, you would entangle it with the walker, and in essence what we would realize then is a spin-dependent translation of the system. And in particular, this is an extremely useful component to think about topology. It has been shown recently that this kind of quantum walking formalism, if you were to do it in a continuous fashion, is actually sufficient for universal computation. So this got us a little bit interested in thinking about this particular protocol. But in terms of simulation, indeed, there's some very nice papers which I'll refer to that says, in fact, one can directly map these topological phases to these type of dynamics. And really, the spin-dependent translation is simply a way to talk about strong spin orbit couple. Right? In fact, this is the ingredient for many modern materials. Okay. So there's this very nice paper. In fact, one of you had also referred to this particular set of authors with Kitagawa and Dembler at Harvard. They have another paper, in fact, where they very nicely prove that if you have a random walk done in discrete time at various steps, this particular algorithm is sufficient to simulate all 1- and 2-dimensional topological phases. Okay, so it's extremely powerful. And in particular, the experiment I'm going to describe today is really for a canonical 1-dimensional topological insulator, which behaves according to the canonical SSH or Su-Schrieffer-Heeger model. And in particular, it's a split-step quantum walk, and I'll tell you a few slides later why we have to do a split-step walk. So this is the SSH model, initially proposed in '79 for polyacetylene, which has 2 ground states, and you can see the position of the double bond tells you about these 2 ground states. And in particular, the band structure here gives rise to block bands with spin texture. Right? So what we see, this is a snapshot of the Brillouin zone. The 2 ground states, if you traverse them across the Brillouin zone, have either no spin flip or the trivial topology, or in fact, they do have 1 spin flip as you go around. So in topological terms, the invariant is the number of twists in the spin texture as you go across the Brillouin zone. So this is indeed a model for a canonical 1D topological insulator. The question now is, how do we encode this type of band structure in a superconducting circuit, and how do I detect this flip? So that's the 2 remaining parts of the talk here. Let's start again with a very, very brief review of circuit QED. The previous speakers have told us about this. So I just have to tell you, in fact, what is my lattice and what is my coin in this particular case. The quantum walk is implemented by a lattice of photonic states. Right? So I take a cavity, I can populate different orientations of coherent states in this cavity. That will be my lattice, my set of points that are there. So in fact, in this particular cavity, I'm going to use 10 coherent states and random walk between them. The coin is, in fact, the superconducting qubit shown here. So I have 1 coin and, in fact, 10 points on a lattice. So the lattice is here, contained in the cavity. This architecture is particularly useful because the dimension of my Hilbert space is a convolution of both of these. So with 1 qubit in 1 cavity, in fact, I can get 22 dimensions. So that's a very, from an engineering point of view, an efficient use of resources, rather than using 22 qubits, say, for doing this type of experiment. Okay. All of it goes down to low temperature, superconducting aluminum within a fraction of absolute 0. A key technology for all of this are home-built quantum-limited amplifiers that allow us to read out microwave fields with cavity occupation of much less than 1 photon, with high efficiency. The coin, the superconducting qubit, you've heard words like transbond qubit, and Neeraj also mentioned nonlinear oscillator, and that's absolutely the right word. What we're constructing here is a nonlinear oscillator where the capacitor is classical. The inductor, if you like, is a tunnel junction, so the current across it is cosine. The current is sine, of course, of the phase difference, and the potential is just the integral of the current, which is a cosine. So all superconducting qubits to date, if you like, are particles in cosine boxes. Okay. So in fact, we have a particle in a box, which is controlled by flux, charge, whatever your favorite parameter is. Okay, but that's the recipe. The frequency of this artificial atom is between 4 and 8 gigahertz, typically, say. The unharmonicity of this system is weak. 5% is typically what you have between level to level, but in fact, it is tunable, as our previous speaker mentioned. That's the qubit, that's the picture of it. So now how do we build in the spin-orbit coupling, right, into this particular system? This is due to the dispersive interaction between the qubit and the cavity, shown here. And in particular, you can write the Hamiltonian where the frequency of the cavity is different than the frequency of the qubit. You get a term for the electromagnetic mode, the bosonic mode in the cavity, the spin of your qubit, shown as sigma z here, and this coupling term shown here, where chi represents the shift of the cavity for every photon. This, in Bendelev's language, is g squared over delta, as we showed you yesterday. Okay. So from the point of view of the cavity, we can probe either the qubit or the cavity. If you probe the cavity, what happens is, in fact, the frequency of the cavity, omega c, is shifted by depending on the state of the qubit. Okay. So the qubit is a two-level system. If it's in the ground state, you will polarize the cavity towards one frequency. If it's in the excited state, you will go to a different frequency, if you like. If you think of it as basically a polarizable two-level medium, which is there. If you probe the qubit, its frequency is stark shifted depending on the number of photons in the cavity. So in this particular regime, it's important to note here that as I put one photon at a time in this cavity, I shift the qubit by more than its line width. So this is this number split regime, if you like. So here's the frequency with vacuum in the cavity, 1 photon, 2 photons, 3 photons, so on and so forth. So I mentioned this because it is important to figure out how to control this system and what to measure in this system. When we would like to execute the quantum walk, we want to flip this coin, we want it to have the same effect irrespective of the number of photons in the cavity. So when we drive pulses on the qubit, for the quantum walk, they are broad in frequency space. Right? So in fact, we affect all of these states together. At the same time, we have the ability to address each one of these lines, so we can use the qubit to figure out exactly how many photons we have in the cavity. And this is a useful tool to reconstruct the Wigner function, or the Usumi distribution of the photonic field. So we can do both things. We can control with broad pulses, and we can in fact read out very accurately and reconstruct the state. So for readout, we have another channel here, which is orthogonal to the control channel, shown as this bosonic field here. Okay. And just to give you an idea of the numbers, the frequency of the qubit is 5.18 gigahertz. The lifetimes, which John Morton defined for us 2 talks ago, T1 and T2 are 40 and 5 microseconds, respectively. The Walker, if you like, this is the cavity lifetime, right? It's 40 microseconds. The interaction between the cavity and the qubit is 1.6 megahertz. So this gives you an idea of how many states I can coherently manipulate before I decay of the cavity. The readout is fast, it's about 300 nanoseconds. So let me show you some cartoons and some data of how this works. We start off with the vacuum state, shown here. So this is the plot and phase space of the cavity. In this polar representation, the circle here represents fluctuations of a coherent state. The length of the vector tells me how many photons I have in the cavity, and the phase of state is simply given by the angle in the description. So my first operation is to displace the state here from vacuum to the red state, okay? And then I flip my coin. And so I go ahead and put a pulse, shown here, a very sharp pulse, on the qubit to create, say, a superposition of any arbitrary angle, and then I let the system evolve. So the dispersive interaction, the coupling between the two, in fact, are going to cause this state to go around on a lattice. And in particular, I'm going to pick points on a circle. So displace, flip, wait, and then repeat. So now I can flip, but I have to flip both parts in my quantum random walk. And then I displace yet again, wait, flip, so on and so forth. Right? And that's how the system is going to evolve in time. So I'm going to execute, if you like, a quantum walk on a circle in this experiment, and there's in fact 10 coherent states that I parameterize here. So I mentioned this term split-step quantum walk. What I showed you, this is the vanilla quantum walk. Right? It sort of simply alternates between flipping the coin and translating, flipping the coin and translating. In reality, I have to have enough knobs to describe 2 different band structures. So the recipe that Kitagawa and Demler have given us is to consider a walk with 2 angles. So I flip the coin in an unequal fashion. Right? So I do 2 rotations with 2 different angles. And if I change the order of the angles, I will get 1 band structure out of the other. Okay? So this is the knob that I have to play with the different topological band structures that are there. Okay? So here's a movie of this particular quantum walk. Preparing it, doing the split-step walk, reading out with the qubit, and then doing tomography where I'm reconstructing now the Husseini distribution, the Q function if you like, in phase space, and that's what's shown here for this choice of angles, pi over 4, 3 pi over 4. This is the system random quantum model. Of course, it does it much faster, but we have slowed it down for you for the movie. Okay, so now if I do it, and this is the final state after you've walked a certain number of steps. If I do it for this choice of angles, again, it will walk. And at the end of this particular same number of sequences, of course, it looks different. It's a random walk to a different set of parameters. So this is the basic functionality. Now the question is, how do I make a simulator out of this? So the particular steps shown here correspond to, again, these rotations and translations. A rotation I can simply generate by e to the I theta sigma x. Right? So this will cause a rotation. The translation, which is spin dependent, is encoded in this type of operator, which is here. And I can think of the unitary evolution of the walk as simply, r times t raised to the power n, which is the number of steps which are there. Okay. So I can think of this unitary, of course, as being expressed as the exponential of some Hamiltonian, right, after some discrete number of time steps, n times t. And in particular, we see that this system has a discrete translational symmetry, right? H will commute with t here. And this is what gives rise to these block bands that we were talking about. And in particular, I can think of the spin-dependent translation as also generated by the momentum operator, e to the ik sigma z. So if I put it together, my effective Hamiltonian has a term e to the ik sigma z and e to the I theta sigma x over 2. So this maps on exactly with this SSH or 1D Hamiltonian. And the spin-orbit coupling is coming from some coefficient, sigma z times the momentum, plus something which depends on sigma x. So that's in fact the precise mapping. So the challenge now then is, in fact, how do I figure out this phase which is accumulated across the texture? So in our system, we're going to perform the analog of a block oscillation. We want to actually traverse this particular Bilbon zone and see what phase is accumulated. The way we do that is rather different than in the system that you've heard about this morning. We're simply going to put another pulse which changes the k vector. Right? So we step through the values of k by putting another rotation. So the protocol now is rotate for the quantum walk, put this additional rotation to get to another point of the Brillouin zone, and then do the translation. Okay? So in that way we can step through delta k and in fact map on those. So this is called a refocusing walk, so that we start on one point of the Brillouin zone, traverse it and come back to the same periodic point which is there. So then I'm going to show you this walk, these two walks after refocusing. So indeed it is going to evolve, and then you'll see where it ends up after we traverse the Brillouin zone. Okay, it comes back exactly to the same point because I've gone through this periodic structure. And now there's a very fundamental piece of quantum mechanics that's going to show up here when I do the same protocol for the different choice of angles. These two walks should encode the two different topologies, and they should have the two different Berry phases. But in fact, I end up with exactly the same answer, right? And the reason for that is a very strong one, in that one should not be able to measure an absolute phase in quantum mechanics. Right? I'm starting off with a coherent state. These topological invariants are not so easy to get a handle on. In fact, they're exceptionally robust to all local deformations. Right? So we need something more subtle, if you like, to detect really the Berry phase which is hiding in there. So what we do in the final part of the talk is not to use coherent states, but to use Schrodinger-Cat states. In fact, to do the quantum walk. So let me walk you through that. The felines are shown at the top here. So we start again with the vacuum state, right? And in fact, what we're going to do is flip it and form the Schrodinger-Cat state. So in fact, the little walker now is going to be these two states, right, that are here. And in fact, I'm going to park one part of the cat onto the third excited level, to the third level. So it's not going to walk. It's just going to stay there fixed as a reference point for me. So in the end, the adiabatic walking cat, one half of the Schrodinger-Cat state is going to go ahead and do the quantum walk. The other half is still parked at 0. So in this way, what I will be able to do is to impart the topology of the state onto the phase of the Schrodinger-Cat state. Okay. And in fact, then at the end of the day, I can unravel this phase, which is there. And you see the difference rather immediately in the WIGNER function, right, of these two iterations. So if I have the trivial topology, this is the WIGNER function that I get with winding number 0. If I look at this state, you can see the interference pattern, in fact, is absolutely out of phase with this one. So we have a very direct signature, if you like, of the topology of this band in this particular method. We can take also a line cut, and you can see very nicely the chain number of 0 and 1, okay, in this particular setup. So at this point, I'd like to point out and make another reference to the nice paper that you talked about earlier this morning about how to measure Zach phases in atomic systems. This is also a measurement, if you like, of this Zach Berry phase and an extraction of the topological invariant, but done with a very different simulation method, right, using a pulse scheme. So where are we going with this? Well, if we have 10 qubits and 19 cavities, which is the architecture of this particular chip, that's quite a large phase space that one can access. And in particular, if we look at the phase space in this periodic table of insulators, there are lots of things to do. We could look at quantum spin Hall, as we described earlier, in 2D and 4D, right? We can go ahead and also look at things that are not so easy to find in nature or impossible to find in nature, such as Hopf insulators in 3D. But beyond that, there's a lot of interesting fundamental physics questions that remain on this type of architecture. For example, if we would like to create entanglement in these structures, at the moment what I've showed you is very simple connectivity. Right? You have two objects that are next to each other. Maybe I would like to entangle object 1 with object 7. Right? And that's not an easy function to do in these particular chips. So one approach is to engineer the dissipative bath in such a way that entanglement can be created at will and stabilized between different parts. And to stimulate questions, I show you only this iconic image here about bath engineering. The other thing to think about is, what do we measure in such a chip? Right? This gets out of control very fast. You have lots of channels to measure, lots of correlations to measure. So we have been thinking over the years about reconstructing quantum trajectories, real-time measurements if you like, but in fact of incompatible observables. So for example, if you have a spin system, you have 3 canonical Cartesian spin operators that you can measure. Heisenberg tells us that there's incompatibility with any pair of those, but that doesn't stop us from measuring them, right? So what if you were to measure Sx and Sy at the same time, what would happen? Right? Can you still extract information from the system? You can, and in fact Heisenberg tells you exactly how to do it, if you think about it. The consequence is, though, the wave function no longer collapses. In ordinary quantum mechanics, we're used to the idea that you make a measurement and you collapse to an eigenstate. This is absolutely given up when you do something like this. And that I show here by this mythical animal shown at the bottom, telling you exactly what's happening in the systems. So these are little pointers for questions if other questions do not arise during the talk. So I'd like to stop here and take questions. Thank you. Okay.
So, curious, how much of the signal do you lose in this process? It seems like what's the fidelity?
Right. So the question is, in fact, how efficient are all the components of the system? A good way to think about that for superconducting folks is to go back to this diagram, which is here. In particular, at the moment, for us, quantum information has to travel from one box to another box, and that's problematic. So if you like, the quality factor of the cavities is extremely high. The losses on chip can be in a regime where they're very small. And in particular, we can be in the regime where most of the information is simply leaking out through the transmission line, which is coupling to the cavity, rather than other parasitic modes. So at the plane of the cavity, everything is good. We can be in the nice per cell limit where things are coming out. The challenge then is that I have a signal of order 1 microphoton or smaller here, then how do I magnify it? It would be tremendously beneficial if we could integrate an amplifier inside the cavity. And then I don't have to shuttle things around. We're working on that, but it's not obvious how to do that. The conventional way is to take a cable and go ahead and go to some external amplifier. This amplifier itself is made of superconducting materials. There's no dissipation. It works very well at the quantum limit. So only the losses that I have are in passive elements going from here to here. So those elements are connectors. Connectors can be very good, just like for optical fiber. The problem is I have these non-reciprocal devices shown with circles here. So if I don't put them in there, I don't have a k vector, I don't have directionality. So microwaves will go back and forth. These rely on a type of Faraday rotation, if you like. So they have magnets, they have other things in ferrites. And they are lossy at the level of 1/10 of a dB or so for the best ones. So that's my only loss in the problem. So the best we've done is 70% of absolute quantum efficiency. Right? So for every 1 photon that I put in, 0.7 of a photon is detected. Okay. For reading out qubits, this is absolutely not a problem. Right? Because all I have to do is separate my histograms so that I can read them out. So that you can get as many nines as you want in fidelity. For doing a weak measurement, where you're actually trying to track a quantum state, every little bit of information that you lose matters. Right? And the way it enters into your estimation is not linear. So we can do still a pretty good job with 70%.
I think this question follows on that last statement. So I was a little confused about how you were taking the Q function measurements sequentially. So you're not making a Q and D measurement in those, right?
It's a dispersive measurement, so it's a QED.
It is. Okay.
Absolutely. In the polariton limit, we would not be making a QED measurement. Right? But in fact, the system is completely dispersive, and there's a second orthogonal mode to read it out.
In your quantum Wonk measurement with the entangled state, how do you ensure that the fixed one doesn't move away?
Yes, this is a very good question. It starts off by noting that the superconducting qubit is not really a two-level system, right? In fact, in that cosine potential, there are 5 levels typically that are there. The 5th one is not so easy to stay in, of course, you would tunnel out and do other things, but the 3rd one is actually quite stable. So there's E, G, and F in that nomenclature, if you like. So what we do here, we start off with a pulse on the qubit, right, making a pi/2 pulse, displace the state here, let it evolve, right? So you let the other half of the cat state evolve here, and at this point I displace one more, right, to bring it in fact to the vacuum level here, and then I excite on resonance with this down state to put that one in the F state. Right? So that one now is shelved at a transition which is off resonance, right? Both from the cavity drive, getting the qubit. So that one will quietly stay there and do nothing until I'm ready to unshelve it, right, at some point where I do this process in reverse. And go ahead and disentangle, and this is sort of the function of the cartoon here. Here, the phase of the topology is entangled with the cat. Here, I disentangle it, right, and leave the cat alone and take the phase out. So it's a manipulation of a 3-level atom. With 2 levels, we couldn't do it.
My question is politically incorrect. I'm not an expert in quantum computing, although I use quantum mechanics every day, have done for 30 years. And within the community, you'll hear various claims about the operational success of various qubit devices, from D-Wave to Martinez to your group. And how can I ascertain, in an unbiased way, the effectiveness of these different claims? What parameter should I be looking for? And how well does your, how many qubits was it? 19? 10 qubit device work on the basis of that parameter description?
That's a great question. It's not politically incorrect, it's a funding agent question. So, for me, I have a very simple, I have 2 interests in this science. One is to study fundamentals of quantum mechanics, which can be done with any number of qubits. And the second one, which at least for me I had sort of shelved away as something I would never be able to do, which is to make something practical out of this. So that view, at least for me, is changing a little bit. And the reason for that is as follows. If I use the simple benchmark of when can I build something that I can no longer predict classically, this for me is now a useful benchmark and metric. Everything that I have done so far I can just solve on a classical computer. Right? So in a sense I'm testing a theory, validating some of the theory. So I made this cryptic comment about quantum chemistry. And this is seen as a playground where, in fact, we could cross this boundary between 10 and 100 qubits. So let me expound on that. If we are trying to solve, let's say, the energy level structure of a molecule, right, the simplest way is full configuration interaction or solving the Schrödinger equation. This one, of course, you run out of memory even with a exascale petabyte computer very rapidly, somewhere between, let's say, 40 and 50 qubits. If you go to a very fancy machine that the DOE will build with 10 petabyte of memory in 2020, it's 47 qubits. Okay. This is an unoptimized code. Condensed matter theorists are very clever, and they have looked at renormalization group methods. Right? So if you do DMRG, certainly in one dimension, you can do Mera-Ansatz tensor networks in more than one dimension, and you can push it up to 75 qubits. Okay, so that's sort of a soft bound. But as I go somewhere between, let's say, 40 and 100 qubits, then I've crossed something where, in fact, I'm no longer able to, with any machine, calculate something. So many of us are targeting that. Now, 40 and 100 is still quite a distance from 10. The chip that I showed you actually is a linear array of 10 that I folded on the chip. The goal for us to do 10 by 10 and get to 100. Right? That's sort of why that chip was chosen that way. But there may be an easier access, which is the idea of dynamics. So if you try to look at the dynamical evolution of a system, you run out of actual processing power on a classical computer much faster than the memory. So the idea is for dynamics with 10 or 12 qubits, since you have to now think about the orbitals and the time steps and so on and so forth, there may be a soft access there. The challenge with the dynamics is what do I calculate? And for the ground state, there are good variational methods, right, that can find the answer. For dynamics, it's not so easy. And this is one of the reasons we also got interested in the quantum walk. What I showed you today is sort of the static properties of the walk. Right? We do the walk, we measure the output. But in fact, the walk is a dynamical process. So if we're able to encode the dynamics of an enzymatic reaction, catalysis, Haber process, whatever you like, ozone dissociation, then that's something where classical methods really fail fast. Okay. So I think that, for me, is the softest entry onto this barrier where a claim can be validated that we can solve a problem which classically cannot find a solution. Is it airtight? Are there no other classical solutions? I don't say that.
No, but you didn't answer the question I asked.
It was a D-wave question, so that's a difficult question.
Well, I wanted to know, for example, whether your 10-bit qubit computer actually operates as a fully operational 10-bit quantum computer. If I gave you an algorithm that only requires 10 qubits, could you do it?
Sure, but the question needs to be qualified. So a 10-bit algorithm, is it fault tolerant or not, say? So for example, if one wants to do fault tolerant computation, right, there are 10 logical qubits that are there. And in this type of architecture, for example, in the Martinez group or the surface code is being validated, you will need, let's say, 1 or 10,000 physical qubits for each one to have error correction. So the question is, do we want to do error correction or not? So this is why in simulation, right, this is without any error correction. So if you give me a code where there's no error correction, of course I can do it. If you give me a code where you want to error correct in a fault tolerant fashion, I would need 10 protected logical qubits, right? And that's a different animal than that's there. So certainly we can run a 10 qubit algorithm, which is 10 straight qubits. If there's something deeper like a fault tolerant algorithm, etc., then you will need more qubits to do it.
I just wanted to add a follow-up comment to that. And you mentioned with the difference between physical and logical.
Yeah.
What I've read from, say, Matthias Troyer and others is that even looking at the molecular simulation, yes, it's 50 to 100 logical qubits, but those are logical qubits, and the actual physical qubits are more like 10 to the 4, 10 to the 6. With a runtime with any realistic system, that it's 1 to 100 days.
This is not correct.
Okay.
So for the following reason.
So please tell me why Matthias is
We have gotten interested in this. This is not correct. Matthias is correct for a certain algorithm. So for example, in chemistry, life started off with something called quantum phase estimation. Right? So this algorithm is exactly as you said, right? And then we were never interested in this for at least a decade, right? Because we would need 1,000 million gates, etc., completely useless, or at least not practical on any time scale. So then the folks at Harvard, Alana Spruguzik, they also came up with the phase estimation. They came up with a better one, which is the variational eigensolver. So, and then we have improved on it yet one step further. So let me talk about those two improvements. With the variational eigensolver, the idea is that if you can take your Hamiltonian and you can express it as a sum of polymatrices of higher and higher order, then you can measure term by term, right, only the correlators that you need, and that would make an approximation to the actual answer you're looking for. So what that does is it's called a hybrid algorithm in modern literature. You're doing only the quantum parts with your quantum machine, and then doing the classical parts with your very good classical computer. Right? So DMRG is this, right? You take a 1D line, you break it up into 2 parts, and then you vary the size of your 2 sections. So that's what we're doing with polymatrices. You solve for the correlators, and then you iterate classically for finding this. So this has now been implemented on a few different machines. So the question is, if you have fewer qubits or shorter lived qubits, is it of any value? So what we have recently added, we meaning Jarrett in Lawrence Berkeley Laboratory, Jarrett McLean, who comes from this LMS-Peruzzi group, came up with an architecture where the number of qubits and the lifetime simply increases the precision of your result and doesn't stop the algorithm from running. Right? So the question is, if I have 10 bits or 100 bits, what's the difference? It's the number of 9s that I can get. And the question is, how many bits do I need to get to a heart rate to do something of chemical accuracy? It's not so many. It's not so many. So with 10, we're more than good enough. In fact, we're doing it with 2, as Martinez has done as well. Right? So with 2, you can get a very useful answer. And in particular, you can also get the reduced density matrix, which is really more useful, even than just simply solving for the ground state. Okay. So I would say, yes, Matthias is correct. Matthias Treuer is, of course, correct in the utility of that particular algorithm. But this is not the state of the art in quantum chemistry algorithms. There are now nice ways where a lot of us are looking at this to get to things that have decent accuracy, that are pretty fast. The challenge is what you said in your little quote of Scott Aronson, right, the uncomfortable truth of quantum computing, which is the question that you're trying to ask, right? Is it globally useful, right? Is it always better, right? Is it always better for a certain class? We have absolutely no answer, for that type of question. Does it have a utility for things that are currently difficult to do? Yes. So the particular machine that you mentioned of certain cases, it does something. Matthias is trying to figure out what it does, amongst others. Right? So I cannot answer the question from the general point of view, does it do everything under the sun? Does it do something, perhaps? Right? And these are, again, targeting very specific problems, not general computational problems.
Great. I think that will close the session.